Okay, this is going to be a quick rapid fire, whole bunch of definitions that you'll need to know. So I'm going to explain all the notation that we're going to need for the DFA section of this course. So first off, string concatenation. If x and y are strings, then just putting them next to each other, x, y, that just denotes the string x concatenated with the string y. So normally we'd write that like this, but in the DFA section of the course we just leave the concatenation operator out and just put them next to each other. Just like when you write like 3 times 2, just like when you write number x times number y, you can leave the dot out and implicitly this means multiplication. So here, putting 2 strings next to each other denotes concatenation. And this notation will make sense in a moment why we choose this. Epsilon is a special character that we always reserve for the empty string. And here's how we define exponentiation of strings. When I write a to the power of n, where a is a character or a string, that just denotes n many copies of a all concatenated with each other. A to the 0 is 0 many copies of a, which is just an empty string. And using exponentiation to denote this is really useful because it follows the index laws you're already used to. N plus m many copies of a concatenated is just n plus m many copies of a all in a row, which is n copies of a, followed by m copies of a, which is the same as a to the n concatenated with a to the m. So this looks like the index laws for multiplication, and so that's why we choose this notation. Next thing I want to talk about is the clean star operator. If a is a set, well first off, if a is a set, then a to the n denotes any string of the form w to the n, where w are elements chosen from a. So for example, if a is the set of x and y, a squared is any string that can be made from exactly 2 characters in a. So xx, xy, yx, yy. And a to the 3 would be xxx, xxy, blah, 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 yy, all 8 possible combinations. The clean star operator denotes any possible string that can be made from characters in a. So clean star is a to the 0, that is all strings of length 0 made from characters in a, so that's just the empty string. Union a1, so in this case xy, x and y. Union a2, so all of these strings. Union a3 and so on. So it's any string made from characters in a. So for example, if sigma was the set containing 0, 1, sigma star would be any binary string that can be made out of just zeros and ones, including the empty string. Okay, so that's what the clean star operator is. Well, that's what the clean star operator is for a set. If it's talking about strings, if alpha is a string, alpha star denotes any number of copies of alpha, including none. So when we write w is equal to alpha star, that's really just shorthand notation to say w is empty, or w is 1 copy of alpha, or w is 2 copies of alpha, or so on. One of these options, right? So this is really, really useful shorthand when you describe a particular collection of strings. And the last bit of notation I have to define is the extended transition function. So the transition function n for a DFA takes a state and a single character and tells you where to go next. The extended transition function takes a state and takes a set of strings and tells takes a state and it takes a string, that is like a sequence of characters, a finite sequence importantly, and it tells you where the DFA will go when it consumes that string. So if I'm in the state S and I read the empty string epsilon, I go nowhere because there's no string to consume. And if I'm in some state S and I've got some string to read that starts with an x, so x is a character, and is followed by an alpha, where alpha is a string. So this notation here you can sort of think as x cons alpha. That's what you should think in your head. Well, where do I go when I read x cons alpha? Well, I see where x takes me by just evaluating the transition function. This thing here is going to be a new state. And then I call the extended transition function again on what's left over. So the extended transition function is a recursive definition. So for example, if we're considering this DFA here, what would, let me pick a different color, I'll use green. What would n star of S4001 be? So 0 is a character, 01 is a string, so you can sort of rip the 0 off the front. This is the same as n star n S4001. 0, 1. So this is my x and this is my alpha. I'm just following the definition of the extended transition function. If I'm in S4 and I see 0, I go to S5. So it's going to be n star of S5, 0, 1. And what's that? That's n star of n S5, 0, 1. And so to get the idea, S5, read to 0, go back to S5. So this is going to be n star of S5, 1. And you keep evaluating it. And well, if you're in S5, you stay in S5. So you keep evaluating it, and you're going to get n star S5 epsilon at some point, because I've used up all the string. And if I'm in S5, there's nothing left to read. That means I stay in S5. So that's how you evaluate the extended transition function. Normally, you don't have to be quite this verbose, but I'm just doing it for pedagogy's sake. Okay, so that's a lot of the notation for this week that you're going to have to be familiar with to be able to answer the questions.